So here is the first sample problem, and let's take a look at what we have. A gas cylinder at room temperature. I'm going to use a highlighter here to kind of go through and get some stuff. I'm going to get this a little bigger. Okay. Gas cylinder at a temperature of 0 degrees Celsius is thrown into an incinerator where the temperature reaches 500 degrees Celsius. All right. So here's another temperature. If the gas inside the container was initially at a pressure, okay, so pressure, this is different. It's at a pressure of 1 atmosphere. What pressure, there's another pressure, did it reach inside the container? Or sorry, inside the incinerator. So this up here, okay, this is an initial temperature. This over here, this 500 degrees, this is T2. All right. This pressure is an initial pressure. We'll call it P1. And this pressure, this is P2 inside the incinerator. And this is what we're looking for. All right. So if I set up my P1 over T1 equals P2 over T2. So this is Guy-Lussac's law, right? I run into a problem. See if you see the problem. Pause it. Think about it. What is the problem here? The problem is my temperature, my initial temperature is 0 degrees Celsius, which means this T1 is 0 degrees Celsius, which makes this whole side of the equation undefined. Last time I checked, that was bad. So that gives you a piece of information, okay? The gas laws are designed to be true for the Kelvin scale. Oh, the Kelvin scale. All right. So that means that I need to convert my temperatures into Kelvin. And if you remember from the last video, well, why don't you pause it and see if you can come up with the values for T1 and T2 in Kelvin. T1 equals 0 degrees Celsius plus 273.15. So that's 273.15 Kelvin. T2 is 500 degrees Celsius plus 273.15 Kelvin. 273.15. So that's 773.15 Kelvin. Okay? And if we're being honest with ourselves, right, this is 500.0. Okay, 500.0, which means that I need to round to this decimal place. And this is 0.0, so I really need to round to this decimal place. Okay, so we'll keep that in mind as we go through the problem. When you solve a problem like this, all right, when you just have an equation, I want you to solve for the variable that, or isolate the equation for the variable that you're trying to solve for before you plug in numbers. This is good practice to get into. It helps you practice your algebra skills, and when you take physics, there are often times when variables cancel out. And you can see that when they're variables very easily. Okay, and it saves you rather a lot of time. So I am trying to find P2. Okay, so I'm trying to find this guy. So I'm going to multiply, well, let me rewrite here. P1 over T1 equals P2 over T2. I'm trying to find for P2, so I need to isolate that. So I need to get rid of this T2. So I'm going to multiply both sides by T2 over 1. Okay, that cancels out this T2. And so my P2, I'm going to flip the equation so I can plug some numbers in. P2 equals P1 T2 over T1. It is very common for people to get a little sloppy with these identifiers and start plugging things in the wrong place. Make sure that you're very careful here. Okay, so P1, if I go back to the problem, P1, okay, is 1 atmosphere, 1.0 ATM. T2 is 773.15 Kelvin. T1 is 273.15 Kelvin. Okay, notice my kelvins cancel out. And my answer, after I do my calculations, is 2.8 atmospheres. And I'm, again, using two significant figures because this value here has two significant figures. Okay? So that is a problem using Guy-Lussac's law.